Now welcome to the next session of chapter 1 linear algebra of the course engineering mathematics. Now in this session we discuss the determinant concept followed by examples and shortcuts. How to manage the determinant of larger dimension matrices within short span of time, right? So here this is concept is examples of determinants. Examples of determinants. We have 5 examples. Let us discuss one by one. Suppose I have a matrix A equal to 1 2 1 2. Now in this context, first row and second row are same. First row is R1, symbolic representation. Last row is notation is R2, second row. Now in this case, the data of this matrix is product of diagonal minus product of non-diagonal. So in this case, the value is 0. So that means in this case, 2 rows are same. Therefore, the value of det is 0. The same case is possible even for 2 similar columns also. So that means whenever you have any matrix, here I started with 2 by 2 matrix, you can go for larger dimensions also. For example, say 3 by 3, 4 by 4, 5 by 5, etc. Any n cross n. So you take any n cross n matrix in which 2 rows are identical or 2 columns are identical, then definitely its det becomes 0. Let us verify by taking two more examples. So in this case, it has only 2 rows, R1 equal to R2, det of this matrix is 0. Suppose if I have this matrix A equal to 1 2 3 2 1 9, this is 1 2 3. Now in this case, first row and last row are same, 1 2 3 1 2 3. That means R1 equal to R3. Now let us verify the data of this matrix. So in this case, the symbols we use is plus minus plus. In the last session, we have discussed the definition of determinant of a matrix by expanding first row. So 1 1 position plus 1 2 minus 1 3 plus. So I am expanding its det by using first row. So therefore this is 1 into det of this particular matrix. So 3 minus 18, this is minus 15, minus 2 times determinant of 2 9 1 3, 6 minus 9, this is minus 3, plus 3 into determinant of this black, 2 into 2, 4 minus 1, this is 3. Now in this case, this is minus 15 plus 6 plus 9. So therefore it cancelled, the value becomes 0. So in this case, the data of this matrix is becoming 0 because first row and last row are same. So therefore here first row and last row are same. Therefore the data of this matrix is 0. Now let us see one more example by taking 2 similar columns. Suppose A equal to 2 1 1 1 4 minus 2. For example, 1 4 minus 2. Here in this case, column 2 and third column are same. That means second column equal to third column. Therefore, the data of this matrix will be 0. Let us verify. Again, I am expanding its det by using first row. So the symbols we use is plus minus plus. So therefore, this is 2 times. Now the data of this matrix. So minus 8 plus minus 1 into minus 2 plus 4 plus 1 into, so this is minus 2 minus 4. So this is minus 6. Now you can see. So let us see the first one. So this becomes 2 times minus 8 minus this minus 8 minus 1 into minus 2 plus 4 plus 1 into minus 2 minus 4, that is minus 6. Now therefore in this case, this is 2 into minus 16, this is plus 2 means minus 2 minus 6. Sure, this is actually 1 minus 4 minus 2. Of course this is not equal to 0 because here I did not take second column, third column are same. Suppose if I take this, if I manipulate this, So this I am going to take it as plus 4. Then you can verify, cross check this. So det A becomes 2 into det of this. So therefore this is 2 times minus 8 plus 8 minus 1 into this is minus 2 minus 4 minus 6 plus 1 into this is minus 2 minus 4, this is minus 6. Therefore this is plus 6 minus 6, its det value is 0. Therefore the conclusion from first example is, in any square matrix, if any two rows or any two columns are identical, then its det value is 0. First work out these examples. Note, in any square matrix, comma, if any two rows or columns are identical, if any two rows or columns are identical, then determinant is 0. In any square matrix, comma, if any two rows or columns are identical, then determinant is 0. Now we discuss second example, second category. In every category we discuss one or two different examples. Suppose I have a matrix A equal to 2, 4, for example minus 6, minus 12. Now here this second row is minus 3 times of this. That means R2 equal to minus 3 into R1. 2 times minus 3, minus 6, 4 times minus 3, minus 12. So minus 3 is a randomly selected number. So here one row is a constant multiple of another row. Now in this case det A becomes 0. This into this minus this into this. So therefore here one row is a constant multiple of another row. So its det is 0. Now let us discuss one more example in the second category. Suppose the matrix is this: 2, 4, minus 2, 1, 0, 2, 2, 0, 4. Now when you observe this matrix, this third column is 2 times of this. So column 3, C3, this is 2 times of this, 2 times of column 2. Now in this context, I am going to expand its det value by using second row. Even you can follow by using first row, or by using second row, or by third row, or by using first column, by using second column, or by using third column. But here in this particular case, I am giving priority for the second row because it contains a majority number of zeros, so that I get the result very easily. So but what are the symbols to be used? So this is in 2, 1 position minus, 2, 2 position plus, this is minus. Of course this is the only non-zero number. Therefore the det of this matrix is minus 4 into determinant of, eliminate this row and this particular column. Then this becomes 1, 2, 2, 4. Now it's det, this is minus 4 into det of this 2 by 2 submatrix is 0. Therefore it is 0. Therefore the conclusion from second category example is, in any square matrix, if one row is a constant multiple of another row, or one column is a constant multiple of another column, then its det value is 0. That constant you can take it as negative numbers. In the first example, that constant I selected as minus 3. In the second example, that constant is selected as 2. Even you can take fractional values, zeros, any number is possible. So the only point is just to check whether any row is a constant multiple of another row, or any column is a constant multiple of another column. In that context, its det will be 0. See, all these points are valid for any n cross n matrices. As a sample, we were discussing 2 by 2, 3 by 3 because they are simple to get the results. But all these points are valid for any general encrossing matrix. For example, if you give me 50 by 50 matrix, suppose 17th row is 6 times of 30th row, then its det is 0. Or for example, 31st column is equal to 1 by 4 times of, for example, 27th column, then that becomes 0, right? Basically, they will be called as linearly dependent columns or linearly dependent rows. We discuss probably in the next future sessions, but for the time being, you try to understand these points. Write this second example. Right, conclusion of this example. In any square matrix, comma, if one row is a constant multiple of another row, in any square matrix, comma, if one row is a constant multiple of another row, or one column is a constant multiple of another column, or one column is a constant multiple of another column, then determinant is 0. See, actually, the first category point is a particular case of this. Here, I am saying, what I am saying in this context is, this is the point Ri equal to k times of Rj, or Ci equal to k into Cj. Suppose if k equal to 1, particular case, then ith column equal to jth column, which we have discussed in previous case. If k equal to 1, ith row equal to jth row, that means when two identical rows are there, then that becomes 0. So therefore, second category example is a particular case of first category example, right? So this is the more generalized case. One row is a constant multiple of another row, or one column is a constant multiple of another column. In that case, that is 0. Now let us move to third category example, which is again more powerful case than case 1 and case 2. Suppose I have an example like this: a equal to 214, 8 2 minus 2, for example 10 3 2. Now when you look at this particular matrix, this third row is linearly depending on top rows. 2 plus 8 is 10, 1 plus 2 is 3, 4 plus minus 2 equal to 2. That means in this case, R3 equal to R1 plus R2. So one row is sum of remaining rows. So basically this is called linearly dependence relationship among rows. This is called linearly dependence relation among rows. So therefore, whenever there is a linearly dependence relation among rows or columns, then its det will be 0. Let us verify that. 2 plus 8 10, 1 plus 2 is 3, 4 plus minus 2 equal to 2. Now let us expand its det value by using first row. So the symbols we use is plus, minus, plus. Therefore, the det of this matrix is 2 times Det of this 2 by 2 block, 2 into 2, 4 minus 3 into minus 2, 4 minus, this is 4 minus of minus 6, minus 1 into det of this 16, minus minus 2 into 10, of course it is minus 20, plus 4 into det of this 24 minus 20. Now therefore this is 2 into 4 plus 6, 2 into 10, 20. This is minus 16 plus 20, 36, minus 36. This one is 24 minus 24, 4, 4, 16. Therefore here the det value is 0. Therefore in this case we have a linearly dependence relationship among rows. Therefore the value of det is 0. Even I can go for some different examples. Here you can see before R1 the constant is 1. Before R2 the constant is 1. So it need not be 1 always. For example, R3 can be 4 times of R1 minus 7 times of R2. You can choose any constants. Here you can multiply R1 with any constant. Multiply R2 with any constant. You can have either plus or minus between rows. Then that becomes 0. Let us discuss one more example by taking columns. Suppose second example in this category. This is first example. Suppose I have a matrix A equal to 2, 1, 4. For example, this is 12. This is 9. For example, this is 8. Suppose this is 6, 5. This is 12. Now in this case, this is 7. 2 plus 12 is 14. 14 by 2, 7. 1 plus 9 is 10. 10 by 2, 5. 4 plus 8 is 12. 12 by 2 is 6. That means second column equal to half of column 1 plus column 3. Now you can see in this example, column 1 is multiplied with 1 by 2. Column 3 is multiplied with 1 by 2. So you can have different constants, but here also I selected 1 by 2 particularly. Therefore, let us see the det of this matrix. Here this is plus, this is minus, this is plus. So det of this matrix is, so 2 times 40 minus 54. 40 minus 54 is minus 14, minus 7 into 8 minus 36, minus 28, plus 12 into, this is 6 minus 20, minus 14. Now this is minus 28 plus 28 sevens, minus 12 into 14. Therefore here this is, it will be 0. You can verify the result will be 0. Therefore in any square matrix, if one row is linearly depending on remaining rows or one column is linearly depending on remaining columns, then det of that matrix is 0. Even I can go for deep examples also. Let me explain through one different example which I am not writing on the board, which is not possible also. Suppose I have a 50 by 50 matrix. I have a 50 by 50 matrix. So assume that the matrix is A. Suppose R17 equal to 2 times of R1 minus 1 by 6 into R3 plus 11 into R14. Suppose the matrix follows this particular relation. So randomly 17th row, see except 17th row all rows were randomly fixed. It's a 50 by 50 matrix. So it has exactly 50 rows. But here I am particularly assigning 17th row based on this particular formula. So here there is no importance for this 2. No importance for minus 1 by 6. No importance for 11 also. So therefore in place of 2 you can take any constant k1. In place of minus 1 by 6 k2. In place of 11 you can take general constant k3. In that case that becomes 0. So whatever the constants you are multiplying with rows or columns, they are immaterial. Irrespective of those multiplied constants, that becomes 0. So therefore this is called linearly dependence relationship among rows or columns. Note these examples. Note, in any square matrix, comma, if one row is linearly depending on remaining rows, if one row is linearly depending on remaining rows, or one column is linearly depending on remaining columns in any square matrix if one row is linearly depending on remaining rows, or one column is linearly depending on remaining columns, then determinant is 0. Then determinant is 0. Next, fourth category example. In this case, we'll try to find determinants of upper triangular or lower triangular matrices. Suppose A is a matrix 2, 0, 4, 3. Now this is a lower triangular matrix. All elements above diagonal are 0. This element is 0, so it is a lower triangular matrix. So here the data of this matrix is product of diagonal minus product of non-diagonal. In this case, we are getting 6. Basically, this 6 is nothing but 2, 3. Product of 2 and 3. 2 is a diagonal element and 3 is a diagonal element. So the conclusion from this particular example is, if something is lower triangular, its that is product of diagonal elements. So this is one example. The second example we use is for upper triangular matrix. Let us take some larger dimension. Suppose A equal to, for example, 2, 1, minus 2, 9, 8. This is 11, 0, 0, 0. Now this is an upper triangular matrix. Here all the elements below the diagonal are 0. These three are 0 elements. So this is an upper triangular matrix. Now since the last row contains majority zeros or first row contains majority zeros, you can expand it either by using first column or by third row. Now I will expand that value by using first column. By using first column, I will try to find its det value. So this is 2 times of det of this remaining 2 by 2 submatrix. So this is 111. This is 0 minus 2. So this is 2 into 1 into minus 2. Here this 2 is a diagonal element. 1 is diagonal element, minus 2 is diagonal element. So basically these are nothing but product of diagonal elements. Here also this quantity is product of diagonal elements. Therefore, irrespective of size of a matrix, if something is either upper triangular matrix or lower triangular matrix, its det is product of diagonal elements. Irrespective of size. I have a 50 by 50 matrix which is upper triangular. Its det is product of all 50 diagonal elements. Write this example. Note, if A is either upper triangular or lower triangular matrix, then det A is product of diagonal elements. If A is either upper triangular or lower triangular, then det A is product of diagonal elements. Last category example, which connects determinant of a square matrix A and determinant of its transpose. Let us take one simple 2 by 2 example. Suppose A equal to 1, 2, 3, 4. Now its size is 2 by 2. So here det A is equal to product of diagonal minus product of non-diagonal. So AD minus BC, it is minus 2. Now the transpose of this matrix is 1, 3, 2, 4. Now the data of this matrix is again product of diagonal minus product of non-diagonal. This becomes minus 2. Therefore, det A is minus 2. Even det of A transpose is minus 2. So the conclusion from this example is det A equal to det of A transpose for any square matrix A. Note this example. Conclusion, if A is any square matrix, then det A equal to det of A transpose. then det A equal to det of A transpose. So let me recall all the last 5 examples. If something is an upper triangular matrix or lower triangular matrix, its det is product of diagonal elements. That is one remark we made from these examples. Another remark we made is from the last example, det of A is same as det of A transpose. And more or less remaining 3 examples are more or less equivalent. If there is a linearly dependence relationship among rows or among columns, then that becomes 0. I think example 1, example 2, example 3, there are more or less general cases, but last 4 and 5 are some different points. Now, suppose if I have a matrix A, if you ask me to find the det of this matrix, if it is a general 3 by 3 matrix, suppose if no 2 rows are same, if no 2 columns are same, assume that there is no linearly dependence relationship among rows or columns, assume that this is neither upper triangular nor lower triangular, then it is simple way to find det of this matrix. As I mentioned in the last session, det can be expanded by finding its cofactors. So in the last session, we have found the determinant of a 3 by 3 matrix just by finding cofactors, capital A11, A12, A13. What is that capital A11? Determinant of 2 by 2 submatrix. A12, determinant of 2 by 2 submatrix. A13, determinant of 2 by 2 submatrix. Basically, this is called recursive definition of finding determinant of a square matrix. So suppose if I follow finding cofactors like this, as the dimension of a matrix increases, then it becomes so complex procedure for me. Then in that case, if at least one of these examples supports, then answer will be very simple for us. Suppose assume that if there are assume that a particular matrix does not belong to any one of these 5 examples. Then what we need to do is expand det of a square matrix by using a row or a column which contains majority number of zeros. Suppose I have a 4 by 4 matrix. Assume that third row contains 3 zeros. Then expand that value by using third row. Then that will be restricted to determinant of a single 3 by 3 submatrix. Got it? I have a 4 by 4 matrix. Third row contains 3 zeros or for example 2 zeros. If it contains 2 zeros, then finding determinant of a 4 by 4 matrix is equivalent to finding determinant of 2 pairs of 3 by 3 submatrices, lower dimensions. Similarly, if I have a 5 by 5 matrix, suppose if a fourth column contains 3 zeros, then finding det of that 5 by 5 matrix is equivalent to finding determinants of 2 pairs of 4 by 4 submatrices. So as the dimension increases, the procedure becomes so complex. Therefore, if any one of these points applicable to such examples, apply them, you get the result within short span of time. So time minimization is very important for us. So suppose assume that if a question is given in the more complicated way, suppose if the size of a matrix increases, definitely there will be some properties behind that particular matrix. So in the future we can discuss determinants of many various submatrices, determinants of orthogonal matrices, determinants of skew symmetric matrices, so various points. So after that, once a matrix belongs to skew symmetric, it has a different determinant. If it is an orthogonal matrix, it has some different determinant. So let us discuss all those points. Okay. Now the next concept we need is elementary row operations. The next concept is elementary row or column operations. We have 3 row operations or column operations. Let us discuss elementary operations for rows. First row operation is this. Ri double implies Rj. This is ith row, this is jth row. The meaning of this is exchanging rows. What we will see is, before exchanging two rows, what is the depth of a matrix? After exchanging two rows, what will be the depth of a matrix? Is there any connection in the determinant of a square matrix before exchanging, after exchanging rows? That is my interest, right? So this means that interchange of ith and jth rows. Let us start with a simple 2 by 2 example. A equal to, for example, 1, 2, 2, 9. Now the data of this matrix is 1 into 9 minus 2 into 2. This is 5. Here I have two rows. There is no chance to exchange. So here I am exchanging, except this case. Exchange first row with the second row. Then as a result, I will get another matrix. Let it be B. Now therefore this becomes 2, 9 and this becomes 1, 2. Therefore the data of this matrix is minus 5. So before exchanging rows, the data of this matrix is 5. After exchanging rows one time, the data becomes minus 5. So therefore, what is the change in the determinant of a matrix? Just it changes its sign. Magnitude is same, but it is changing its sign value. How many times rows have been exchanged? Exactly one time. Suppose if this operation is applied two times, again I will get the same matrix. Again that will be same. Therefore, if I interchange rows exactly one time, that is affected by minus sign. If I interchange rows two times, there is no change in the depth of a matrix. That is very clear. In case of a 2 by 2 matrix, just to find the depth of this matrix, we are getting 5. Now in this case, we have only one alternative, that is exchanging first row with second row. There is no other chance. Therefore, in this case, I am getting a new matrix B. So how we are getting this matrix B? By exchanging first row and second row. So the determinant of this resultant matrix is minus 5. So magnitude 5, but sign is plus, this is minus. Therefore, when you interchange rows exactly one time, the depth is affected by minus sign. Suppose if you interchange rows two times, depth is affected by no sign. The same depth will be acting continuously. Therefore, here one time, two time, that means how many times we are exchanging rows, whether it is applying odd number of times or even number of times. So if rows are exchanged odd number of times, depth is affected by negative sign. If rows are getting exchanged by even number of times, there is no change in the depth of a matrix. Let me give you one general example. Suppose I have a 4 by 4 matrix, 4 by 4. Assume that the depth of this matrix is 18. Now in this case, suppose if I apply this, I am exchanging R1 with R4 and I am exchanging second row with the third row. So that means rows have been interchanged two times. So 2 times means even times. So when rows are exchanged even times, I am getting a new matrix B. Again its size is 4 by 4, but in this case the depth of this matrix will be again plus 18. You can see one important point here. R1 is exchanged with R4, R2 is exchanged with R3. No matter which rows, how many rows are getting exchanged, but only point is how many times the rows are getting exchanged. Here R1 is involved, but here R1 is not involved. R4 is involved, not R4. So all the rows are different. So no matter what the rows are getting interchanged frequently, only the point is how many times the rows are getting exchanged. So if the rows are getting exchanged even number of times, no change in depth value. If the rows are getting exchanged odd number of times, that is affected by minus sign. Note these points. First one, Ri double implies Rj. Interchange of ith and jth rows. Interchange of ith and jth rows. The above operation changes depth value by minus sign. The above operation changes depth value by minus sign. The above operation changes that value by minus sign if it is applied odd number of times. If it is applied odd number of times. Next point, the above operation does not change that value. The above operation does not change that value if it is applied even number of times. If it is applied even number of times. To justify this note down this example. Simple 2 by 2 example. Always start with 2 by 2 examples and then you generalize, you will get points very easily. Now let us go for second operation. The second operation is this. Ri implies k into Ri. So ith row, the k is some constant. What does it mean? We are multiplying ith row with some constant k. Multiplying ith row with some constant k. That constant can be negative or positive or 0 also. Generally we don't take zeros because when you multiply a particular row with 0, so the entire row becomes 0, that becomes 0. So it's an obvious thing. So let us take k value either positive or negative, because when k is 0, that means we are multiplying one particular row with 0. In that case, all elements of that row become 0. So in that case, the data of that particular matrix will be 0. It is a silly, very trivial issue. So let us do not take k value 0. K can be general number, non-zero number. Now let us see what will be the changes in the data of a matrix before applying this and after applying this. Again, we start with a simple 2 by 2 example. Suppose I have a matrix A equal to 2, 1, for example 8, 9. Now the data of this matrix is 2 into 9 minus 8 into 1. 18 minus 8, this is 10. Now here I am taking R2. R2 implies 4 into R2. So that means only second row is multiplied with 4. As a result, I am getting new matrix B. Its size is again 2 by 2. But first row will be as it is. This is 2, 1. Only second row is multiplied with 4. So 4 8 is 32 and 4 9 is 36. Therefore, the data of this matrix is 2 into 36, 72 minus 32 into 1, so 32. And this becomes 40. Basically, this 40 is nothing but 4 times of 10. And you can see this 10 is nothing but data of original matrix. And this 4 is nothing but this constant. Therefore, when you apply this particular operation, the data of resultant matrix is affected by this much k times. Got it? Now in this case, we have manipulated only second row. Like this, you can implement the same rule for all rows with all different constants. We discuss shortly. Meanwhile, note this point. Ri implies KRI. Multiplying ith row with some constant k. Multiplying ith row with some constant k. The above operation changes that value. The above operation changes that value by k times. The above operation changes that value by k times. So basically, this 4 is nothing but this constant, this 10 is this. So here we can write it as 4 into this 10, I can write it as a. Note down this example. Now, let us try to implement same operation for different rows by taking different constants also. Suppose I have a n cross n matrix A. So here R1 is multiplied with some constant K1. R2 is multiplied with some constant K2. R3 is multiplied with some constant K3 and so on. Rn is multiplied with some constant Kn. So all these constants can be different, they can be same. Few constants can be same, few can be different, or all can be same, all can be different. Let us discuss various cases. So here A is the n cross n matrix. First row is multiplied with constant k1. Second row is multiplied with k2. Third row is multiplied with k3. Last row is multiplied with kn. So when you apply all these operations at a time, I will get new n cross n matrix B. Now the data of this resultant matrix B is nothing but k1 into k2 into and so on kn into det A. This is one useful point. Now in this case, suppose if all constants represent single constant, suppose if k1 equal to k2 equal to and so on equal to kn equal to some constant k, this implies data of this matrix becomes k into k, because for all rows every row is multiplied with k. So k into k, how many times? N times. Therefore this is k power n into det A. So when all first row is multiplied with k1, but basically k1 is k. Second row is multiplied with k2, but k2 is k. Like this, every row is multiplied with k. Therefore, this matrix B is obtained from this matrix A by multiplying with constant k. Got it? Therefore, this B is nothing but the matrix obtained from A by multiplying whole matrix with constant k. Therefore, this B is nothing but Ka. So, data of Ka equal to k power n into det A. This is very, very useful result. This n represents size of this matrix A. Note these points. Now, if A is a n cross n matrix, then det B equal to k1 into k2 into and so on kn into A, where B is the matrix obtained from A, by applying the operations R1 implies K1 R1, R2 implies K2 R2, R3 implies K3 R3, and so on. Rn implies Kn Rn, where K1 comma K2 comma and so on Kn are some constants, where K1 comma K2 comma and so on Kn are some constants. Another consequence of this row operation. Note, if K1 equal to K2 equal to and so on equal to Kn equal to K, if K1 equal to K2 equal to and so on equal to Kn equal to K, implies det B equal to K power n into det A, implies det B equal to K power n into det A, implies det of Ka equal to K power n into det A, implies det of Ka equal to K power n into det A. Now we discuss third category operation, that is Ri implies Ri plus Krj. Here K is any constant but I not equal to J. So here ith row is getting modified. Ith row equal to ith row plus some constant into another row. Now let us see what are the changes in the value of a det before applying this, after applying this. One simple point is, here K can be any constant. One simple observation, ith row equal to ith row plus some constant into jth row. Here ith row is not matching with jth row. That means current row is equal to current row plus some constant into another row. So if K is any constant, suppose if I take K value 0, that means ith row equal to ith row, no changes in the row, therefore no changes in the det value. So when K equal to 0, no change in det value. Suppose if K equal to something different, let us take an example. Suppose A equal to 1, 2, 3, 4. So the data of this matrix is minus 2. Suppose I am applying R1 implies R1 plus 2R2. So therefore the new matrix is B. So 1 plus 6, 7. 2 plus 8, this is 10, this is 3, 4. Now you can see the data of this matrix is 28 minus 30, it is minus 2. So original det is minus 2 and its det is minus 2. Therefore, when you apply this operation as many times as you want, no change in det value. Note this point. Ri implies Ri plus Krj, where K is any constant and I not equal to say. The above operation does not change det value. The above operation does not change det value even if it is applied any number of times. The above operation does not change that value even if it is applied any number of times. This is wonderful result. Particularly this result is very useful in making majority entries as zeros. So once majority of entries become 0, getting that value is very simple. Note this example.